Okay, in a previous video, we derived the differential equation that will allow us to find the orbit of an object under the influence of a central force, and we did that and we got this as follows. So an object of mass m under the influences of a central force F of r is given by r, where u equals 1 over r satisfies this differential equation. So we have the second derivative with respect to theta of u plus u equals this term minus 1 over the mass times h squared, where h is a constant, times u squared times this F of 1 over u. Great, so we want to look at an example today where the central force is the gravitational force. Great. So it's well known that Newton's law of gravity tells you that the force exerted by an object with mass capital M on an object with mass little m is given by the following. So it's minus g times capital M times little m over r squared. So where m is the mass of the large object, m is the mass of the small object, and so on and so forth. So that means the right-hand side of, and then maybe let's call this equation number 1. 1 can be written as follows. So notice that can be written as k over h squared. Okay, great. So let's see how we can see that. So notice r squared is really 1 over u squared, so that puts the u squared up in the numerator, and that's going to cancel this, and then the little m's cancel, and then we can combine the capital G and the capital M into a constant k. So I'll just say here k is equal to some constant. Great. So that means our differential equation for u is as follows. So this is the second derivative of u with respect to theta plus u equals k over h squared. Great. And we're going to need a homogeneous solution and a particular solution. So a homogeneous solution to this differential equation can be found by looking at its related polynomial. So its corresponding polynomial is given by the following. So usually I use u as a variable for those, but let's use v because we've already used u. So this is v squared plus 1 equals 0, which has roots v equals plus minus I, which tells you that UH, meaning the homogeneous solution, is given by a number A times cosine theta plus B times sine theta. And now we don't have initial conditions here, but let's just say that we could choose our coordinate system so that our initial conditions are built in a way that makes b equal to 0. So I'm just going to go ahead and write that down. This is equal to a cosine theta, by a choice of coordinate system and initial conditions. Great. So now we have the homogeneous solution is just a times cosine theta. Okay, now the next thing we need to do is find the particular solution. So notice this is a constant polynomial. So in general, we would choose a constant as a guess for the particular solution. In this case, there's not much to it, because if we let u of p be just this constant, notice its second derivative is 0, and that is the particular solution itself. So u of the particular solution is just this constant k over h squared. Okay, great. And now that gives us the entire solution is given by the homogeneous part plus the particular part. So we can write that as k over h squared plus this constant a times cosine theta. Okay, good. And then we can write this thing as the following. We can write, that means r is equal to 1 over k over h squared plus a cosine theta. Good. So I'll clean up the board. This is technically the solution to our orbit, but I'll clean up the board and then we'll talk about the solution a little bit more carefully. Okay, so previously we had proved that the orbit traveled by this object in this gravitational central force is given by the following. So r, as a function of theta, is given by 1 over k over h squared plus a cosine theta. Now what we want to do is set these equal to some other constants, which will make it look more similar to what you might find in a textbook. So if we set rho equal to k over h squared, or sorry, h squared over k, and then if we set e equal to a times rho, then that means we're able to write this r as the following. So this is equal to rho over 1 plus e cosine theta. Good. And then in this case, E is called the eccentricity of the orbit. And let's just notice some important points for E. So if E equals 0, we get R equals rho. So rho is a constant, and if r equals a constant, that's a circular orbit. So this gives us a circular orbit. Great. And then if e is less than 1 but bigger than 0, this gives us an elliptical orbit. And then if e equals 1, this gives us a parabolic orbit. And then finally, if e is greater than 1, that gives us a hyperbolic orbit. And then finally, we have two other numbers attached to this orbit. So the perihelion is given by the minimum distance between the object that is exerting the central force and the object that is orbiting the central force, and that is given by rho over 1 plus e. Okay, good. And then the anhelion, which is given by the largest distance, is 1 minus e. And now notice that can easily be given by different values of this angle. So if we take theta so that cosine is 1, we get this. And if we take theta so that cosine is -1, we get the other one. Okay, good. So that's the end of this example.